The next speaker is Corentin Schreiber from Oxford, who's going to take us to the early universe and talk about quenching and quiescence there.
Thank you. So I'm Corentin Schreiber, and I'm going to tell you indeed about quenching and quiescence in the early universe. Most of the work that I'm going to be talking about today is stuff that I did in my last postdoc in Leiden University with working with Ivo Labbe and Carl Glazebrook in particular. So Katie has done an excellent job at giving introductions, so again, I'm probably going to be quick on this, but I'd like to spend a little bit of time on what I mean by quiescent galaxies and how that relates to quenching. So throughout this talk and in general, when I think about a quiescent galaxy, I mean a galaxy that has an abnormally low star formation rate with respect to some reference that you have to define. And so this means that you can see galaxies that have a star formation rate that is low in the absolute sense, or perhaps relative to its past. So it means that this selects pretty much anything from very old early type galaxies to young post-starburst galaxies. So one way to see this is one reference star formation rate is the galaxy main sequence that you see highlighted here, which is populated by star-forming galaxies. And you can identify quiescent galaxies simply as those that have a star formation rate that falls significantly below what you would expect purely from just random fluctuations of the star formation rate in that sequence. So here I'll be focusing mostly on high redshift galaxies for several reasons. The first is that at a high redshift, the universe was different than it is today. So, for example, the effect of environment was perhaps not as strong as it is today, because at, say, a redshift of 4, you have no clusters of galaxies. Galaxies were also more gas-rich. There were perhaps some more mergers. So you're probing a different part of the parameter space in terms of what could trigger the quenching in the first place. Here I'll be talking about galaxies at redshift of 3 to 4. So the universe there is about a couple billion years old only. So there is no room for slow quenching processes at that time. All the galaxies that you see that are quenched then must have quenched rather quickly. So you're also probing more galaxies that go on that path rather than the other. And what's very interesting is that actually most numerical simulations or semi-analytical models predict that quiescent galaxies should be relatively rare at those epochs. So you can see examples here from this is, I guess, Illustris, and this is Mufasa. The number densities of the objects is very low. So it's a good observational test to see whether those galaxies actually exist, and if so, how can we explain their existence in ways that models don't necessarily predict correctly at the moment. So the way we find quiescent galaxies in general, and this has been, again, described very carefully by Katie, is first by looking at their colors as one way. So in particular, a diagram that is used very often in the high redshift literature is this U minus V and V minus J color diagram, which allows you to pre-select quiescent galaxies in this region here, which have red colors because of old stellar populations rather than dust obscuration. But of course, if you want to be sure that a galaxy is truly quiescent, you need to see spectroscopy of the object. So typically what you want to see is Balmer absorption lines, this is calcium, Balmer absorption lines, no emission lines, and also red spectral breaks here. But this is, of course, more costly, so you can't just go ahead and get spectroscopy for every high redshift galaxy. So you have to pre-select first those that have potentially red colors for quiescent galaxies, and then follow them up. So we played that game with a sample of about 24 galaxies that were selected in the Z-Forge survey, which is a deep cosmological survey of about, I think the total area must be less than 0.2 square degrees. So it's still a relatively small area on the sky. And so here I show you the SEDs of all those galaxies, and you can see this very clear Balmer break here showing up pretty much in all the cases. So they would be typically what you call the post-starburst galaxies with signs of A-star populations. And we followed them up with Mossfire with about 4 hours of integration to be able to see those rest frame optical absorption lines in the spectra. And so to summarize very quickly what the outcome of this experiment, first, we were able to confirm the redshift for about half of the sample because, in fact, all of these were only photometrically selected in the first place, so we didn't even know if they were actually high redshift galaxies, but they were, except for 2 outliers, which turned out to be dusty galaxies. But also what was very interesting is that in most of the cases, the galaxies showed no sign of emission line, which was also a good reassuring sign that they were indeed quiescent galaxies. One of them was, in fact, particularly interesting because it turned out to be the record breaker for quiescent galaxies at redshift 3.7. This was published by Carl Glazebrook and myself a couple of years ago. And I will come back to this object a little bit later. But if you stack all our quiescent galaxies for which we could get a redshift for, you see this very nice spectrum where you see all the Balmer absorption series, calcium H and K, very little O3 or O2 emission, which is also a good sign. This little emission that you see here could very well be powered by just other sources of ionization, so maybe an AGN, maybe evolved stars. But if it's star formation, it's really at the low levels here. So that is reassuring. This means that there are indeed quiescent galaxies in the higher universe, high redshift universe. But the next question is then to compare two models and see, do they predict that same amount or less or more? So what we did then is to apply the exact same selection criteria to models to select galaxies as massive at the same distances and with the same selection for selecting quiescent galaxies. So here in particular, we used the specific star formation rate. And we removed from our observations a fraction of about 20% of contaminants, which we estimated from our spectroscopic campaign. And so here I'm showing examples of predictions from two models that were kind of selected to span the two extremes in the range of what models predict. And so what I found in the end when doing those comparisons is that most models actually fall short of our observations. So this one is particularly the worst because it predicts a number density that is 200 times lower than what we observe. But this one was the only one that actually came close to our actual value, just falling short by a factor of 2, which you would say within the uncertainties is probably acceptable. So this is the Meraxis semi-elliptical model by Quinn et al. 2017. So what's special about this model in particular? It's not clear exactly why it succeeds so well. Maybe one hint is that actually, compared to most of the other models, it was calibrated or tuned to match observables at high redshifts. So it's actually a semi-elliptical model that's made for studying the reionization epoch, so redshift to 7 or 8 galaxies. And so maybe by forcing the agreement to the data at higher redshifts, it's perhaps favorably biased to match our data better. But still, it's not perfect because we have spectroscopy for those objects. We can also do age dating, and we can compare the properties of the stellar populations we see in our galaxies compared to what the models actually predict. And there is a stark disagreement there. The average age of our stellar population age of our galaxies is about 300 million years here, but the models predict that actually the vast majority of their galaxies have quenched only less than a million year before being observed. So those galaxies are indeed found in the right number, but they're still way too young compared to what we see. So this means that we don't necessarily understand still how those galaxies are formed that early in the universe, a redshift larger than 4, actually. So to try to understand a bit more about the channel through which these things formed, we can look a little bit more detailed into one object in particular. So this is the record breaker galaxy that I told you about earlier, which we nicknamed Jekyll. You find a reason why in a few moments. So it turned out that actually, when we observed this galaxy with ALMA, it turned out to be detected in the submillimeter, which is probably a bad sign because it means that you have hot dust, dust powered by stars, star formation actually. But it turned out actually that the ALMA detection was offset from the galaxy very clearly, and it was coming from a separate source that was like a fraction of an arcsecond apart. And those two things are extremely compact, less than a kiloparsec across. So I guess if you're used to low redshift galaxies, I guess this is a pretty small size. But nevertheless, those two things are really massive. So they are the same redshift with just a slight velocity offset. So they're probably perhaps interacting. Either they have interacted in the past or they will be interacting. But now that when we got the position of those two objects, we actually could do force photometry and all the rest of the multi-wavelength data that we had to try to get more ideas of the property of that source. And so what we found is that so this dusty, weird object that is actually, you cannot even see it at all in the HST images. It is similarly massive compared to this quiescent galaxy companion. Both are stellar masses of 10 to the 11 solar masses. But what's very different about it is that it has a very strong attenuation, about 3.5 in AV, which is one of the largest values you ever find in galaxies. But yet, despite its super large stellar mass and super strong attenuation, it's not forming a lot of stars apparently, because in the far infrared it's not extremely bright. And so if you do a careful joint modeling of all the photometry of the object from the ultraviolet to the far infrared, you find that the actual star formation rate of that dusty galaxy could be anything from 0 to 120 solar masses per year. The reason for that is that actually, because it is so obscured, most or all of the stuff far-infrared emission could be powered by just intermediate-age stars that are still heating the dust that's in the galaxy. So that may be actually a sign that the galaxy has quenched. We still don't know because, indeed, the range of star formation rate here is actually pretty large. So the galaxy could be a normal main sequence galaxy or a quenched galaxy at this stage. But the possibility is open for it to be quenched. At most 200 million years after, we would be observing at most 200 million years after it died. So that's actually very interesting because those two galaxies being apparently so similar in most of their properties, except that the one has dust, the other has not, and maybe they have a slight time delay between their evolution. You could maybe draw an evolutionary path between those two things. So one schematic diagram is where you would have those two galaxies that formed earlier as being strongly star-forming semi-limiter galaxies, and then some event caused the quenching to happen. Then you would see something that looks like this guy here, which has a reduced star formation activity, and then slowly evolved into a more clearly quiescent object here. So this actually comes back to a little bit to what Katie was saying, because if this picture is true, the fact that we see so much dust in this galaxy means that, means that the galaxy quenches before it removes all of its dust and gas reservoir. So that would be an interesting to look into. So to try to probe this in a little bit more detail, we have obtained a bit more ALMA observations towards these objects that I'm going to show here. Most of the data is still to be observed and will come this summer, so unfortunately I can't show it to you. But we got some of the data already. And so what we obtained in particular were spectral observations of the C2 and N2 emission lines. And the ratio of these two lines actually tell you how much of the gas is in the ionized versus neutral phase. And if you look at the plot here on the top right, so normal star-forming galaxies or semi-limiter galaxies at high redshift typically have a relatively low ionized gas fraction of about 20%. So most of the gas that is traced here by C2 is located in the photodissociation regions surrounding star-forming regions. But on the other hand, if you look at the galaxies which have the highest ionized gas fraction here, those are mostly early-type galaxies in the local universe, or more secular or quiescent, slowly star-forming galaxies at redshift 0. And so what we found is that actually in this galaxy, we were able to resolve the emission line profile of the galaxy, although the signature noise is still a bit low. But we find a tentative evidence that, although as you see, the error bar is a bit large, that the gas in the very center of the galaxy, so less than, like within the half-light radius, is essentially predominantly ionized, which is, again, something that we only see in old or quenched galaxies, while the outskirts of the galaxy is clearly more neutral. So this would suggest that there is some form of inside-out quenching, where the galaxy stops forming stars possibly in the center and then progressively from the towards the outskirts. As to what could be causing this ionization, it's still pretty unknown at this stage. It could be a remains of an AGN, or maybe radiation from the very tightly packed stars that are in the galaxy. But at this stage, we don't know. So I'm running over time, so I'll just leave my conclusions here and take questions.
Thanks, that's really lovely stuff. Questions? Becky? I thought I was going to get a chairs question then, but no.
Okay, so forgive my high redshift ignorance, but at one point you were saying that the star formation rate that you'd derived between like 0 and like 120 solar masses a year, you said that was anything from like a quenched galaxy to a typical main sequence galaxy. Yes. Is 120 solar masses a year a typical main sequence at that redshift?
Actually, this 120 is a factor, like it's a 40% lower than the main sequence. So star formation rate they are really high values at high redshifts. I guess I should have shown that, but
yeah. I didn't realize it got that high.
Yeah.
I would have thought that was still like a starburst or something, like, and that would have been with like one.
No, starburst would be
quench.
the thousands of solar masses per year.
Okay.
Yeah.
Thanks for clarifying.
So I think I will take my question because
sure,
it's so similar. Yeah. So what struck me there was just seeing so clearly in that slide that to you at high redshift quenching takes you down to sort of 10 at the least, right?
Yeah.
And so I guess my question is, are there any reasons to expect that the same mechanisms that could do that take a local galaxy from a few down to not a lot? I mean, it seems to me those should be treated as completely different processes.
I believe that's actually true, that there's very likely two different kinds of mechanisms that operate at different epochs. Like a lot of people talk about this slow versus fast quenching processes. I'm pretty sure that's what it is, right? And indeed, you can't fall down from 1,000 solar masses per year with a slow quenching process all the way to 10 or 1 or even 0 solar masses per year. So yeah, these are the two channels. I think that they are indeed different processes. So that's part of the reason why I want to look also at high redshift.
Yeah, good. One more question if there is one. Stunned by brilliance. Thanks, Corentin. Thank you.
Thank you.